Right, thank you very much. Right, the presentation for this evening is artificial ground freezing, to be presented today by Dr. Christian Gilbert. Christian studied civil engineering in France before doing a master's and a PhD in civil engineering in Northwestern University in the US. He joined SYSTRA 10 years ago as VP Structures and Civil, and was previously our Director for Engineering for Solitaire Battery Group. He has more than 25 years' experience as a contractor and specialising in ground engineering. He's also been elected President of the CEN TC 288 in 2012, and was the French representative for the execution of the standards and convener for 2 other standards. He's also a member of the Executive Commission for Dams in France. In parallel, he's taught for more than 30 years in many engineering schools in France and other universities. He's published more than 30 technical articles on a variety of subjects, including rock stability, diaphragm wall projects, ridging inclusion, soil dynamic behaviours, and many, many others. Over to you, Christian.
Thank you. So good evening. So thank you to be here. We will go through artificial ground freezing. This is a technique which is not often used or used when engineers are totally desperate, which happens sometimes. We will go from the beginning, meaning what is artificial ground freezing, before going to project. So the first part that we will review or discover as a function of your own experience are the principle of the technique. Then we will go through 2 classical examples. Example of cross passages, or that we will see, one in Paris, one in North Africa. And then we will go through a full project, which was very challenging, and we will review all the techniques which were used on Metro Line 14 in Paris, leading, in fact, to a successful project after, I would say, some observational method and modification of projects, because this is life of project, in this case, when we use this kind of technique. And then we'll conclude quite shortly on what I believe brings this method, which is not a method which can be applied on the shelves, but which is based on observation. So first of all, the principle. The principle, in fact, is to extract it from the ground. We will see how we extract it from the ground. When we extract it from the ground, the groundwater, which means that we need water in the ground, saturated is better, saturated ground, will be converted to ice, and this is this mix, in fact, which is called ground freezing. This mix has a strength which is increased. We'll see what kind of increase. It goes to water tightness of the medium, of the soil which has been frozen, and it allows safe excavation. Where is it applied? Is it applied? This technique is quite expensive. We'll see later. But compared to other techniques, in fact, this is an additional technique to be able to excavate in safe condition. And it is used when other techniques, like grouting, cannot be used. So, for example, it's not in competition because of the price with grouting, depending, in fact, on what we grout in the soil. But it's used, in fact, when it's non-groutable. So if we have fine material, fine sand, sand with silt underwater, and we need to do an excavation. In this case, grouting being not applied, cannot be applied in this condition, and ground freezing can be a technique which allows, in fact, to do the excavation safely. Obviously, ground freezing, which is a soil improvement method, is for temporary structures, and it ensures, as I said, structural strength and water tightness. So the principle, you can see it here on, we'll start here. So in fact, you have a supply line. So in fact, you are putting a pipe in the ground. This pipe is sealed in the ground, so outside. We send a fluid under low temperature. This fluid, in fact, transfers the negative heat to the ground, okay? And the ground, so, decrease its temperature. The ground will decrease its temperature and will get frozen to a given temperature that we will see. How is it done? It is done with a fridge, like the fridge that we have in our house. We have a cooling agent, which, if we use water with salt, is called brine. So this is a salty water. We'll see the composition later on. It's compressed. Then it's vaporized, and when you vaporize it, in fact, you are decreasing the temperature. The temperature at the fridge side, when it gets out of the fridge, can vary between -30, -35, -40, depending on the salt content. As you know, the more salt you get in water, the harder it is to freeze. Okay? And this fluid goes into the pipe that we have seen here and transfers the cold toward the soil. So this is the main principal technique. The typical projects are cross passages. So for cross passages that we'll see later in a real project, we try to put in place tubes where brine will circulate. The brine is going to freeze the soil, hopefully continuously, because if it's not continuous, we have a water tightness problem. And we can excavate inside without any water inflow if the area which is frozen is continuous. So this is a very simple principle. What is important, just to give figures and you know where we are going, is a kind of UCS, so unconfined compressive strength of this material at the end. This is in MPa, so directly we can see it. You see, for example, in sand, usually we freeze at about -10, the soil. The fluid is at -30, but globally the soil is at -10, -15. The strength, UCS, is in the order of 7, 8, 10 MPa for sand. And what you can notice from lab test is that the UCS, the unconfined compressive strength of this frozen body, in fact, decreases when you get more clay and silt, so small size particles. Okay? You can see that, for example, for clay, you get under -10, you get 5 MPa, silt 2 or 3 MPa. What is also interesting is that for ice, pure ice, UCS is kind of lower than the mix with the soil. Okay? You take these values for short term, because the story is a little more complex, but if you take a frozen soil directly, you test it in lab, you test it quite fast, obviously, you are not going to wait to load the sample, you'll get this strength. So just a few figures, and the figures are not to be reminded, I just want to show you the necessary energy that you need to freeze 1 cubic meter of soil. And afterward, it will be very important to design, in fact, the power which is necessary, so the energy per second, which is necessary to freeze a soil. So we define the specific heat capacity. This is, in fact, the work or the energy which is necessary per kilogram, so this is the unit of mass of soil, of material, whatever the material, and per degree. So if you want the change in temperature of 1 Kelvin, 1 degree Celsius in this case, it's the same, per kilo, this is the unit of energy of joule that you need to put. This can be defined as a function of the kilogram or cubic meters of material. You have the change of phase of the water, which is called the latent heat. And you see that to change 1 cubic meter of water, you need this value, which is 336 megajoule per cubic meter of water. And you have thermal conductivity, because when we do calculation of area of influence of a freezing zone, you need to know what is the conductivity of the heat. We call it permeability when we do dewatering. We call it thermal conductivity when we do it for energy of temperature, which goes into the system. Another figure to compare is the energy of nitrogen, N2. So, two ways of putting cold. Either you use a mix of water and salt, okay, which is called brine, or you can use nitrogen. There are advantages on both techniques, we'll see later. 1 cubic meter of nitrogen, nitrogen is liquid under minus 196 degrees and goes to gas to minus 80. So when it passes from minus 186 to minus 80, the energy released is 250 megajoule. Okay? So it means that, for example, you need a little bit more than 1 cubic meter of nitrogen to freeze 1 cubic meter of water, if the water is at 0. And still in water, at 0 minus, you need 336, so it's 1.1, 1.2 cubic meter of nitrogen. So now let's see the properties. So here you have the material. So to be clear, the material is, when I say clay, this is clay particle. Okay, this is not a mix with water. So we are sharing the material, the sample of clay, or the sample of sand or silt and so, into one part which are soil particle, and one part which is the water. Because we'll see that the energy goes a lot into the water to be frozen. So the air has low conductivity and a volumetric heat of 1.2. We just have to remember why, because the unit weight, so the density of air is 1 kilo per cubic, 1.23 kilo per cubic meter. So not a lot of matter. There is absolutely not a lot of electron and nucleon. For water, the conductivity is 0.6. For particle of clay is, let's say, 1 point something, the range. For the silt is 2, sand is 2, clay is 2. Okay, so more or less, there is not a lot of variability. It's between 1.4 and 2, 1.5 and 2.5, but very close values. In terms of volumetric heat, you can see that water, to change 1 cubic meter of water by 1 degree, the temperature by 1 degree, you need 4,000 kilojoules. Then, for all particles, you see the distribution. It varies, okay, but slightly. So this is just for you to understand the big masses of energy which is transferred in this process of soil freezing, so that you can do the calculation by hand. You don't need computers for the first trial. Then we lack computers, so we do it with computers. So as you can see, for clay particles, silt particles, sand particle, clay particle, in fact, globally the same. Okay? In unfrozen state. For ice, you see that the conductivity is 2.3, so it's not so different from the particle of soil. The volumetric heat is 1,800, so it's a little less than for the clay or soil particle under a frozen state. And for the frozen state, it's still more or less the same. You see, it's 2.3, 2,300, 2,200 for volumetric heat, which means that we need about 2,000 kilojoule per cubic meter of silt particle in the frozen state, compared to 3,000. So very close. When you want to do a rough calculation and to see how heat and energy distributed in the process of freezing a mass of soil with water. As you see, and as you know, the conductivity of steel is very high. You don't put a steel bar into the fire and take the steel bar by the hand without protection. This is usual. And the volumetric heat capacity is 3,800, so not so different. So now we'll do through a small exercise, because the result is always the same. What is very important, in fact, is this. The energy to freeze the soil depends on the latent heat by transforming water to ice, so around 0 degrees. It's a lot of energy. And how much is it in the real case? If you take a sand, so you take 1 cubic meter of saturated sand, temperature, initial temperature is 20 degrees. Final temperature is -10. I will explain to you slightly later on, why I'm choosing -10 degrees. With water content of 25%. So the porosity is for 40-something percent, 45% if I remember well. The total energy required is 220 megajoules. But how is this energy distributed? To change water into ice, so we go from 20 degrees to 0 plus, to 0 minus, change of state, to -10. So this is a state of 0 plus to 0 minus for water. 60% of this total energy is used to transform water to ice. Then, to transform water from +20 to 0 plus, and from 0 minus to -10, it's about 20%. So I rounded up the figures because it's 22, 23%. It has no interest. The big interest is this one, which means that just for the water, to transform the water into ice from +20 to -10, you get 80% of the energy. 80%. So the remaining is the change of temperature of the soil structure. So here it's sand particle. You take the sand particle from +20 to -10. It represents 20% of the energy, roughly. So if you don't want to bother, just compute what is the water content. Easy. And then, okay, plus -10, 20%, plus 20%, that's all. But what also is very important is energy is dictated by water content. So low water content, lower energy, high water content, a lot of energy. And in this case, the part of the solid change in temperature, so the soil particle change because of temperature, is smaller. So the more water content, the more you get into the water, the less water content, the more it is. So this is very important. So for example, when you want to get this project, you just compute. First of all, you define the soil. When we work with soil, it's always difficult if we don't have any data, reliable data. But as soon as you get a reliable data, you find the water content. You want to, because of design, have an annulus of, let's say, 1 meter, because the stresses in this annulus when you excavate works with 1 meter. In this case, you compute the volume, and you get directly this volume. You compute the volume of water, you get the energy at 80% of what is required. So this is then we can do a lot of more refined calculation. But in terms of energy, this is the way for a good pre-design. So in conclusion, water content is very important because the change of state takes a lot of energy. If you get cavities in soil where you want to freeze, the consequence is what? Cavity is full water, no soil, nothing. So you need a lot of energy, a lot of energy. You don't want to spend money in giving energy to water, so what do? You grout. You fill the cavities for many reasons. The first reason is you decrease the water content, so the quantity of water in the cavity, and in this case, you need a lot less energy for freezing. High water content increase the energy which is required, and in this case, the duration of duration, because the power of the freeze unit is given. So for a given power, if you need more energy, you need more time. And to reduce porosity, some treatment, grouting, may be needed also, always to reduce the quantity of water. I will take the opportunity to say an additional stuff which is later on, but which is related. Let's imagine water is flowing. So you get natural current in the ground. If the velocity of water does not allow the water to take the energy of freezing because it flows, in this case, you don't freeze the soil. Water will be with a temperature which is lower, but will not have time to reach zero. So you can put a lot of energy, but you will, I would say, cool the water, but not freeze the area that you're interested in. So in this case, you need to decrease the velocity of water in the ground. And we will see it with the last example, real example. And you need to treat the ground so that its permeability is low enough so that the speed of water allows a contact between in the frozen area, in contact with the tube of freezing, so that you can create ice. Now we are going to see the properties, and the properties of ground freezing, in fact, are very important because this is a strange material. This is a material which creeps a lot. So it's not like, it's like concrete, but unfortunately it drops quite quickly and very fast. So first of all, let's see this diagram. So this is a test, no confinement. So the two principal stress, sigma 2, sigma 3 are 0. The sigma 1 principal stress is vertical. This is under triaxial no confinement. And these are the temperature. So as you can see, so on the horizontal axis, this is a strain, actual strain, and this is a stress. This is what happened at -2 degrees. In fact, as you can see, so UCS is what is 2 MPa. If you do the same, if you use the same sample under -10, it's 8 MPa. minus 15, 11, minus 20, 13. So first of all, the lower the temperature, the higher the UCS, the unconfined compressive strength. Now, let's see what happens when we load a sample with different strain rate. So in fact, now you are pushing the sample, so you are dictating the strain as a function of time, and you are crushing the sample. So on the horizontal axis, this is a strain. On the vertical axis, this is a vertical stress applied to the sample, no confinement. This is still a UCS here. And the sample has a temperature of 10 degrees, minus 10 degrees. These are not the same sample. So what happens is the strain velocity is quite high. So we are crushing the sample at a rate of 1% per minute. UCS is, there is a peak, but let's say is about 13 MPa. If you are crushing slowly at 0.01%, it's 8. And if you are crushing at 10 to the minus 1, 10 to the minus 3, sorry, per minute, it's 6. So you see that between this 1% at 13 and this 10 to the minus 3, you get a ratio of 2. So the loading, we know that loading is important. And when we crush a sample, we crush sample with a given speed. But here it's quite important. It means that if the loading of the soil is very low against the frozen area, then you'll get less strength, less UCS. I will go here before coming back to the previous slide. What is also interesting is the following. This is a diagram where you get in the horizontal axis the time of loading. On the vertical axis, you get the strain of the sample. When you load your sample with 2 MPa of stress, this is how it evolves in strain. It's quite stabilized. You load it at 3 MPa, it's still stabilized. At 6 MPa on this sample, you see that it's stabilized, but it tends to go upward. At 7, it really goes upward. At 8, it goes upward very quickly, 9 and 10, and so on. Now, if you plot this result into this diagram, so you see the temperature is minus 10, and you take the slope. Okay, so the slope is epsilon dash. Okay, this is the strain velocity. So epsilon point, it's strain velocity. You plot it in this diagram. So horizontally, it's time still, and then this diagram is the slope of each loading case. This is what happened. So the strain velocity, you see that for 1 MPa, the slope is quite constant. Okay, 2, 3, so on. What you see is that there is a divergence, so an increase in velocity strain, epsilon dot, at this point. So it means that the slope is changing. This slope changing, in fact, tends to be for the same strain level. Which means that here you go very quickly to failure. Here you'll go less quickly to failure, but you'll start diverging. The slope, the phenomena has been engaged for the same strain. So now I go back to this, because this is the result. So if here this is epsilon, or epsilon dot, so the strain velocity, this is the time on the horizontal axis. So when you load a sample, initially, you get you increase your strength, then it stabilizes, the slope is constant, and suddenly, when you get a given strength, the slope increases. Now, if I plot the strength, so here the slope is increased and decreases, the slope is constant, okay? And then at this point, the slope increases. So what is interesting to see is that for frozen soil, in fact, there is a given strength at which the sample diverges. It starts creeping at high speed. So in laboratory, when we test the soil, in fact, we try to define this slope, this epsilon, because if we don't load it a lot, so if we load very slightly the sample, in fact, it doesn't reach the critical strength, and in this case, it's stable. But in this case, you need a very thick frozen area to resist the weight of water and soil, which applies under the annulus, for example, in a cross passage. If you load it quickly, or if you load it to 6 MPa, for example, it will diverge. But what is important is, can we, with creep, keep the strength under the critical strength so that there is no divergence? So if your structure of frozen body, frozen soil, is loaded for, let's say, 6 months, what we do is we compute what kind of stress can be applied so that after 6 months, the strength induced by creep does not reach a critical strength. Okay? So what has to be remembered is that it creeps a lot. In order to limit the creep and the creep, the acceleration of creep, in fact, we have to limit the stress. And we'll see what is a factor between a UCS, which is done on a very short term, and the long term that we are looking for 3, 6, 8 months of excavation. Another information is the following, just to have order of magnitude, is unconfined compressive strength of sand, as we saw before. You can see that it's between 5 and 20 MPa in this range. And the more fine you get in the soil, the less UCS you have. So for clay sand, sandy silt, and silt. And the range of engineering, it's always interesting to know, is, let's say, ground between -2 and -15, -20. This is not the range we are using in civil, because in order to cool to -100 or -150, we need to use nitrogen, and it will only cool down on a very small area next to the pipe. But you can see the behavior and the UCS, which is limited in most cases at some value, even though the temperature decreases. And finally, for the creep phenomena, here you have, in fact, the shear stresses. So this is the shear stress which is developed with different kind of tests. It can be UCS, it can be triaxial compression. It's easy to find the maximum shear stress defined in the sample as a function of combination. So we have uniaxial, we have tension, compression, pure shear, and triaxial compression. What you can see is, so here, how do you read it? You read it from the following interpretation. Here is time to failure. And here is normalized shear stress, which is developed at failure. If you load it suddenly, in fact, what is the maximum shear stress which is developed? So you load it at failure suddenly. What is the load which shall be applied to load it to fail directly at t equals 1 second? Okay? By the load, you get the shear stress, maximal shear stress. And this is normalized to this maximum shear stress. So you do it with a lot of sample, with obviously less load, and you find out that if you want a failure at 16 hours, in fact, the maximum shear stress that you shall apply is about, I don't see it, but is about 0.4 of the maximum shear stress for failure at 1 second. Okay? This is a creep. Exactly the same phenomena explained differently with different diagram, but always the same phenomena. Which means that if I do a triaxial test or UCS compression, I find 10 MPa for sand, frozen sand, we saw 5, 10 MPa, let's say 10 MPa. At 16 hours, if I want failure at 16 hours, in my design, I take 4 MPa. See the difference. So we have divided by 2, a little bit more than 2. Fortunately, this is asymptotic, and we don't divide by 100. Usually it's between 2 and 3. Okay? But the result of UCS short term is an indication, but in terms of design, as a function of the loading time, you need to decrease the allowable stress, and this is not even the allowable, this is the stress at failure. Then you need to take a safety factors. Okay? So this is what is kind of particular with ground freezing. So still another order of magnitude of when using this criteria. So in soil freezing, depending, there are projects, very, very specific projects where we use brine. We have actually one project in Australia with tube spacing is 2.5 meters. This is with nitrogen, so very specific. Usually, it's about 1 meter spacing, regular project. And as we said, if the flow of water is too fast, the water cannot go from liquid to solid. And what is the actual velocity where you don't need to do something? If you use brine, in fact, it's 5 meters per day. So if the flow has a speed which is more than 5 meters per day, you cannot use brine. You will not be able to freeze the soil. So you have to reduce the permeability or use nitrogen, because the limit is between 15 and 20 meters per day. If it goes even faster, either you can grout to decrease, in fact, the velocity, or do something else. But it won't work. And as we said before, cavity is kind of important in the technique. If you get cavity, either you fill it, or you don't use ground freezing. Now, the technique is known to have some effect, local effect, small effect, on the environment. When you freeze the soil, in fact, there is a front of freezing. And so the front of freezing is the area, is the surface between frozen soil and unfrozen soil and water. Okay? So this is the difference between the ice part and outside the ice part. When you freeze, in fact, there is a suction which is created, a cryogenic suction. This cryogenic suction, in fact, is exactly the same as the capillarity phenomena. Capillarity phenomena, you know, in soil, we get capillarity water table, which in this area of capillarity, in fact, you are not 100%, you are 100% saturated in some areas above the water table. And there is a part above this 100% and the water pressure is negative. This is why even in cohesionless soil we have cohesion. And we are lucky most of the time to have this cohesion for projects. And above this 100% saturated water area, in fact, we have unsaturated. And this unsaturation comes with capillarity also. So the water, in fact, you can imagine this area of being very small tubes, like when we were at university doing doing experiment on capillarity. Very small tubes where water is going up naturally. It's a function of, it's a contact problem between the tube, if the tube is clean, not clean, and the water. And also the type of water, if it's contaminated, not contaminated, and so on. So this is capillarity forces. When the soil is gravel, when it's high permeability, big grains, in fact, capillarity tends to zero because the size of the pipe, equivalent pipe, is very large. You see, for example, if you take a glass of water, kind of long, you never see the water going up. Capillarity goes to zero because, in fact, the contact is very small relative to the volume of water. If your contact is very high, is large compared to the volume of water, capillarity develops and water goes up naturally because of this contact force. So the rougher the material, like gravel, the less capillarity, in fact, you get. So you see where is gravel, this sand, gravel. You don't have, in fact, the water coming to the front. If you have fine material, in fact, you get severe frost action, which means that the water flows directly to the front of the frozen area. You get more and more water, and lengths of water, which become ice, accumulate to this front. In this case, you get heave. On the opposite, when you get very impervious material, water which tend to flow by capillarity, because the tubes are very small, in fact, cannot easily progress because, in fact, the permeability, the pores are not continuous, or if the continuity exists, in fact, the travel to progress is very long, and in this case, the water does not arrive. So either, and in this case, you can see that the frost action is negligible. What is very dangerous is this silty sand, fine sand, where permeability is low, but not low enough, and the size particle distribution is very small. And this is why in some projects you get heave because of the front where water accumulates, and everything heaves when we freeze some areas. This is the same diagram, except that horizontally this is permeability, but here this is the frost pressure. This does not develop like this in real life. Huh? This is lab test, because so I will explain later on. So you see here, so sand 10 to the minus 3, 4, 5, 6, 10 to the minus meter per second. As you can see, the frost heaving pressure. So what is the experiment? The experiment is triaxial, where you allow the water to come into the sample, you freeze the sample, water is coming, but you restrain the sample to heave. So you confine it, like with odometer test, and you apply a pressure so that the change in volume of the sample is 0. So this is the pressure which is developed. In this case, in fact, you see, for example, for, let's say, silt, I'll take silt, so 10 to the minus 6 meters per second, you get 400 kPa. If you take clay, if it could, it takes time, you get 1,000 MPa. Don't be afraid, this is not what happened in reality. But this is what this test sample shows. If you do a test in lab, this is what happens. We know that there will be water coming, but what is not taken into account in this kind of apparatus, in fact, as the water expands, because it takes more volume under ice state than water state, in fact, the water which is next to it is expelled on the side, and therefore we are not accumulating a lot of pressure. What I forgot to tell you is that, obviously, but everybody knows it, the change in volume of the water is 9%, going from water to ice. And this is why it tends to increase in volume, and it tends to, in fact, make everybody heave, everything heave around it. And finally, what is interesting is to see the effect of saturation. As I said, all these figures that we have seen are for saturated material, which is all voids are filled of water, by water. If we have it, the UCS, or the deviatoric stress, which is the same, so the Q in the Q diagram, the deviatoric stress is maximum when we get saturation of 100%, and if the soil is not fully saturated, in this case, the deviatoric stress at failure, in fact, does not develop, because in fact the sample has no UCS or very little UCS, unconfined compressive stress. Obviously, if you don't have any water for sand, there is no UCS. Okay. So these are the main bases of understanding that we have to have for a project. Now, two ways of freezing the soil. Either we use nitrogen or we use brine. So for nitrogen, on site, this is very important, we have silos, isolated silos, which are filled many times a day, depending on consumption, with nitrogen. You can see here, and nitrogen goes into the bore, the pipes. If we use brine, we have a fridge, so this is fridge unit. The fridge, in fact, decreases the temperature of the liquid. So we are not using sodium chloride because the temperature is only -18 before freezing. So this is salt water. We are using calcium chloride or temper, which is a trademark, which goes to -40, which means that the temperature, when it goes out of the fridge, is at -40 or -35 usually. And this temperature at -45 goes into the pipes that we'll see in 2 minutes, goes down, goes up, goes to the next, goes up, and so on, and in fact decrease the temperature of this area where the pipes have been installed. In terms of power plant of the fridge, it goes from 100 kilowatt to, let's say, 1,000 kilowatt. What is interesting is to see the power of this. 100 kilowatt correspond to 1.5 cubic meter of nitrogen. So what does that mean? It means that if you want to freeze in a few days, you use nitrogen, because 1 cubic meter released per hour is enough to this plant. For 900, it's 900, so it's 10 cubic meter per hour. So it's not a big volume. And it's equivalent to the very powerful freezing plant. So if you want to freeze very quickly, you use nitrogen. There are pros and cons for nitrogen. As you know, nitrogen, we have a lot of nitrogen in the air. But nitrogen is very dangerous. We have 80% of nitrogen in what we breathe. At 86, 87%, it becomes dangerous. And at 90%, we are dead. Okay? Because we need 16% of oxygen to breathe normally without doing a lot of effort. So this is why there are a lot of counterexamples. But this is why we try not to use nitrogen into tunnels, if possible. So we have projects where we use nitrogen, but we have to be very careful in terms of safety to detect nitrogen concentration in the air, because it goes very quickly. So a few years ago, we never used nitrogen in tunnels, at least unless we were in very more than desperate situation. Today we see projects with use of nitrogen into tunnels. But obviously safety process and procedures have been, I would say, evolved obviously positively for the workers into tunnels. Now, this is quite important also. Now, a lot of things important. Huh? I will try to make it easy. This is a pipe which is used for brine and nitrogen. So I will explain the sequence of work. First of all, we drill a hole into the soil and we put a pipe. Okay, metallic pipe. This is a drilling tool. I have to cut? Ah, yes. Okay. Thanks. Yes, because we have 80. Okay, I will go quickly. So, first of all, we are excavating, putting a pipe, and sealing the pipe. What you have to understand is, if the pipe is not well sealed against the soil, the cold does not propagate. So, in fact, you have to seal, to use a good mortar, in fact, a bentonite cement grout, to make sure it sticks against the soil. Some problems, if it's not well done, in fact, the frost will not propagate, and you can do whatever you want, it will do nothing. So this is very important. This is obviously on the contractor side, but we have to follow it. So this is the same. So this is a pipe for the hole. Inside the hole, we put a second pipe. This is general because there are obviously other techniques done as a function of countries where they use the same external pipe for as a second pipe. But in this case, you put an additional pipe that you grout against the initial pipe which was used for drilling, and you put this blue pipe inside. This is for brine. So the brine is coming inside the small pipe, the blue pipe, goes down the hole and goes upward between this annulus, in this annulus between the blue and the yellow pipe. Exactly the same for nitrogen. What is the difference is the center pipe is very small. Why? Because, as we said, the change, the calories which are brought by nitrogen correspond to the change of phase of nitrogen between liquid and gas. We don't want the nitrogen to go to gas when it goes down the pipe. We just want the nitrogen to go into the gas state when it goes up the pipe. So we use a small pipe so that nitrogen is not decompressed, while there is a huge annular space here, the S annulus. When the nitrogen goes upward, there is a change in volume. It goes to gas, and it cools the area. For the brine, this is different. You have a big pipe, so in this annulus, the brine is going downward. This is laminar flow, so no loss of energy. And when it goes upward, it goes between this annulus, between the blue pipe and the yellow pipe. We have less section, higher velocity. It goes to turbulent mode. And in this case, there is a lot of exchange of energy between the brine and the yellow pipe. And it goes to the frozen state. So this is a difference. In terms of corrosion, we have for the brine and liquid nitrogen. For the brine, PVC is okay for the annulus, so the blue one. For liquid nitrogen, PVC breaks because the temperature is minus 190 degrees. And the inner pipe, for central tubing, copper, the copper, there is corrosion, while it is okay for liquid nitrogen. So when we use the two techniques on the same project, because usually we can use the first technique is to put a lot of energy very quickly so that we freeze in a few days, and also it limits the upward movement due to the frozen process. We use liquid nitrogen for a few days, and then we go back to brine, in fact, for the next stage during the full work of excavation. So now, the example. So this is a Paris metro. This is, in this area, you can see a tunnel. This is a tunnel for the rolling stock, in fact, to be stored while waiting their use. And we want to connect here to a building. So these are, in fact, the soil is very, very fine sand, which is not groutable. There is 18 meters of water, so we cannot excavate like this. In this case, we have this path, about 1 meter spacing of tubes, which are drilled horizontally. We are using brine. The tubes have this shape, and obviously it stops here. I will show you the cross-section under this tunnel, existing tunnel. The cross-section of the freezing point is this one. So in fact, we close it. But unfortunately, we finish in the jet grouting area. So the drilling goes from here to the jet grouting area. But here, we still have an unfrozen area. So we were obliged to put drillings for frozen area from inside this existing tunnel. So I will show you the picture. So this is the front of the shaft where we did the drilling. And you can see here the insulation of the tunnel and the additional drillings to connect the tunnel where we couldn't obviously go through the tunnel with the drilling, continuity of the drilling to connect to the jet grouting area. So this ensured, in fact, water tightness of the excavation. Okay, so this is the excavation. This is, the change in section. So where we are not under the existing tunnel, this is with this shape. And when we go to under the existing tunnel, in fact, you see the vault or the raft of the existing tunnel. This is a rectangular section which is excavated. Okay? So this is a very typical project. Another project in different condition. We didn't talk yet to influence of salt in 2 words. The more salt you get, the harder it is to freeze. Water freezing is difficult. And you know that water does not freeze, or the freezing point of water with 26% of salt is minus 20. So if you get a lot of salt, it's difficult. Here, this is in North Africa, a project, 50 meters of water. So now this is not a joke, 50 meters of water, very fine sand, cross passage of 20 meters between 2 big tunnels, 15 meters diameter. Temperature of soil in hot countries is higher than in Europe. It was 25 degrees. High salt content, freezing temperature is -5. So in this case, what we were looking for is temperature of the frozen body of -15. So a lot of compressive UCS were done to find out that the frozen soil of -15 had the required shear UCS or shear strength for stability when we were excavating the tunnel. But in this case, we had sand with 50 meters of water, 500 kPa water pressure, a lot of water pressure in sand. So we cannot play with it. We use brine, temperature -37. The unit, the fridge unit, was in a tunnel because this was for cross passage. Distance between freezing pipes, 1 meter. You can see here the freezing pipes, as well as the temperature gauge, which were put between the 2 main tunnels. And we drilled from one tunnel to the other and tried, this is very theoretical, to be as close as possible to the other tunnel, opposite tunnel. So on drawing, it's 7 centimeters, it was whatever. But what we had is to control the temperature on this side. Instrumentation is very important in this project because, in fact, what we discovered is that we could not freeze this old area. The full area, contact between the tunnel, where all drilling arrived, could not be frozen. And what we discovered, it was not easy, is that there was one pumping well still working at the end of the tunnel, in the box next to the tunnel. So the grouting, the contact grouting with the segment was not perfect, as it is usually, not so perfect. Water was flowing. We were not able to freeze. And this was discovered because, in fact, we had enough instrumentation, measurement of temperature inside the body of frozen soil. And by back calculation, now I'm pushing a little bit calculation. By back calculation, the measurements were very different from what was expected in terms of temperature. Very different. We had to investigate, and in fact, we had even to reinforce energy in this area for freezing the contact. How did we do? So these are the freezing pipe, as you can see. So 50 meters of water required in terms of safety and annulus, which was about 3 meters. And the because we had 50 meters of water, 500 kPa, okay? Plus 50 meters of sand submerged is 500 kPa. So we had a pressure of 1,000 kPa, 1 MPa, over a thickness of frozen soil of 3 meters. And as we have 3 meters and 3 meters, so the radius is 6 meters. When you do the calculation, average stress in the frozen body is 2 MPa. And it was open for months. So we were obliged to decrease the allowable stress to 2 MPa in the frozen body, in fact, and to have a 3 meter thick frozen area, frozen annulus. So we needed, in fact, 2 lines of drilling to get this 3 meter thick annulus. So the effect of salinity is quite important. If you get 8% of salinity, so just in seawater, you get 30 grams per liter of salt. So it's 3%. Okay? In this where we were, we had a little bit more of 30 grams per liter. So for 8% of salinity, the freezing point is -5, which was our project. And under -30 degrees, in fact, UCS is 3.6 MPa. But if you have a salinity of 32 degrees, the freezing point is -20, and the UCS is 1 MPa compared to 3.5 MPa. So you see that at some point, if you get too much salinity, too much salt in water, in fact, it's a little bit difficult. But you never get 30%. This is a theoretical where it doesn't freeze anymore. So what we noticed, it was very interesting. In fact, when the water was freezing, because it was moving, it let some salt, which was not dissolved, in pockets. And when excavation was done, in fact, we had water flowing, not outside of the frozen area, but the water was flowing. And in fact, the water was flowing while the temperature was -19. Because we had a salt concentration in some areas between pipes. So this is what happened when we have this kind of salt content. So how did we cater for this problem of freezing the contact? What we did first is to isolate. So we isolated the cross passage so that there is no change of heat between the tunnel, which was very hot, and the cross passage. This is one way of protecting against the heat. But also, we put a brine circuit at the contact of the segment of the main tunnel, where we had, in fact, brine circulating, so that, in fact, we were trying to freeze, in fact, the segments at the contact, so that the soil behind it went to freeze. So all this obviously took some time to put in place and also to find out. And in this case, we were able, in fact, to freeze the contact, because, in fact, this is quite usual in the longitudinal direction. Whoops. In the longitudinal direction, so in this direction of the drilling, it's always very difficult to freeze. This is why we try to be very close to the segment opposite to the drilling. If not, it takes a long time. So this is the second example, which is kind of excessive in terms of water pressure. 50 meters in sand is not every day. But you see that in the first case, we had 18 meters of water. We had one row of drilling with 50 meters of water, 2 rows. So these are the freezing of the soil. You see the sand, which is totally frozen inside the cross passage. Now, this example in Paris. So this example, okay, belongs to the extension of the Paris Metro, and this is line 14, which is a fully automated line of metro. It was extended north, and this is one part. So the line is 6 kilometers, 4 stations, 5 ventilation shafts. We are just, because we want to go out, we are going to concentrate on only one problem. The issue is the following. This is a station, which is here. Okay. This is a shaft on this side, and we are going to create, and the metro shall go here, while we have an existing line, which is in this direction. So I will show it like this. Plan view. This is a station on the left-hand side. This is a shaft. There is an existing metro line, which was built in 1980, the 1985. And we construct a line, metro line, which shall be below this existing line, crossing from the station to the ventilation shaft, and so on, and continuing. This station, existing station here, of this metro above, is strange. This is a box with very short diaphragm wall, resting on barrettes. But as we are always lucky, barrettes are obviously here. So this is the first luck. So you can see that we need the new metro line to cross here in this direction. We need to go through this box with the metro, or it's exactly an RER. So this is a high speed. This is a train from to go to the neighborhood of Paris. Yes, resting on barrettes. These barrettes, one will be cut, because if not, we cannot make the train circulate. One will be cut, and we'll see how we do it. One will have to remain it here, but we'll have to slide if everything moves inside the box that we are creating. And one has to be reshaped because one part of this barrette is inside the new box and one side is outside. So we need to cut the barrette. This is a cross section. So this is the box that we want to create. These are the two boxes, and the train is going to this direction like this. This is a barrette which is going to be cut. Existing barrette here and existing barrette here. The ground is marl and limestone. Fracture limestone, hypermobility. Sand, very fine sand, not groutable. Clay sand, not groutable. Sand, not groutable. And here, kind of pervious material, marl and gravel. The box is 8 meters high, 26 meters long, and at the end, what we want is a box which has a roof, a base slab. On the roof, the barrette which was cut has to transfer the load to the roof of the box, and then to transfer to the side of the box. So these are the soil, as you can see, very fine sand, clay sand, sand, very, very fine sand, not groutable. Now we are going back to what we have seen. It creeps a lot. When you do UCS test, very short term, you get 6 MPa for the sand when it's frozen. Design value is 2 MPa, 2.5 MPa. For clay sand, the strength is less, as we saw before. It's 4.5 MPa. We take 2.2 MPa when we take the creep phenomena in consideration. Modulus is about 100 UCS, and a little less, 50 UCS when it's clay. Initial solution was kind of simple, but very difficult to put in place. Was first of all grouting below the slab of this area, metro, existing line. So grouting 2 meters below a slab, you don't put pressure. So if you don't put pressure, you don't grout. So the result is difficult. Freezing the soil on the side and doing jet grouting in the marl and gravel from the side before constructing the station and the shaft. But with inclined bore logs, very complicated, and not ensuring, in fact, water tightness of the grouted slab, jet grouting slab. So this solution was challenged, and the solution which was developed is this one, using freezing wall and replacing jet grouting slab by an arch frozen soil. Having drains, and this is what was done. In order to do it, it was done from the station on one side. The distance to be done is 26 meters. It's a little bit long when you do horizontal drilling because you deviate. And so it was decided to do drillings on both sides, for 15 meters on one side, 15 meters on the other side with recovery. And this is what was done, and you can see here on this picture. So this is vertical, so horizontal drilling, and the arch at the bottom from the station. This is what happened. There was another issue, which was uplift stability. And for uplift stability, in fact, excavation was done sequentially. So a gallery number 1, lower gallery, then it was backfilled, gallery 2 and 3, backfilled, so that there was no uplift during construction. And I'm going fast now. Huh? And we see here, in fact, a general view of the excavation. The freezing pipe were at 80 centimeters and 65 centimeters. The analysis, so the analysis for temperature distribution showed, in fact, that the time for freezing was equivalent and everything was frozen at the same time. Particularly, we wanted to freeze very quickly, so the first phase of freezing was done with nitrogen, taking a few days only, and then the maintenance was done with brine. So this is what structural analysis, so strength of material and safety on strength of material was giving. In fact, in this kind of soil, in this kind of project, we consider that the resistance of the frozen soil starts with temperature which are below -10. And everything which is below -10 is considered at -10. So these are the thickness which was anticipated, are thickness of 80 centimeters at the end, minimum 80 centimeters. 80 centimeters for excavation and 80 centimeters for water tightness. We could have done something a little bit trickier, but taking more risk, because here we had stability for uplift. We could have decreased the temperature here in this area, because this is just for water tightness, to -2 degrees. So there are other projects. When we do -2 degrees, -3 degrees, that we did in Paris for another station, to ensure just water tightness, preventing water to flow into the excavation. The top for excavation was frozen to help, in fact, phase stability. We had obviously instrumentation, so measurement of temperature. We had sensor chain to measure temperature. We had, you see, this is inclined, going through the frozen area, frozen zone, to measure the temperature every 2 meters. So out of 10, every 2 meters, you get a sensor, and this chain of temperature is drilled on both sides. On both sides, you get 12 meters of chain of measurements. There was a grouting which was done in this highly pervious area, but unfortunately, it didn't work. Because, as I said, when you try to grout with a cover of 2 meters, 3 meters below slab, in fact, nobody wants to put a lot of pressure, and the grouting pressure was 200 kPa. So with 200 kPa of grouting pressure, due to the presence of the base slab, in fact, you don't grout, you grout nothing. And we got in fact, at the end, water coming. So we were obliged to do something. So these are the drilling pattern, and the red one are the temperature monitoring. In this project, always monitoring. So these are the quantities. What is important is instrumentation, because safety is related to instrumentation. This is an observational method. We change project. If it doesn't work, we adapt. Drains inside the excavation. Why? Because when we freeze an area, a closed area, the water tends to expand, and excess for water pressure comes into the closed area. We need to drain this excess for water pressure. And this is one way of making sure that there is no hole in the frozen body. If not, you cannot control.
5 more minutes.
Yes. So these are the picture of drilling with blowout preventers. This is a full 3D of drilling holes, as well as instrumentation in red. And this is very important to measure deviation, because what is important in ground freezing is the distance between pipes. So if the pipe deviate, in fact, you may have, and the calculation, the full calculation, thermal calculation, is done with the real location of each pipe, so that we know, at least we can anticipate time to be frozen. On this project, we were very simple. We use this kind of axisymmetrical formulas. So this is exactly equivalent to when we do dewatering. Dupuy formula, so let's not spend time on this. And we define 2 levels, orange and red level. What we wanted is a minimum of 80 centimeters of thickness for frozen soil. In fact, we had an alert level when we get 1 meter of frozen soil, and 1 alarm level when we were at 90 centimeters. In fact, the design was done for 80, but we needed to anticipate the thickness of the frozen soil so that, in fact, we had time to put back, in fact, the nitrogen if necessary. So this is why we define 2 levels of careful, alert, and alarm. So these are the temperature as a function of time. And these are, here, the mix, so the temperature which were relevant. As long as the temperature measured were below the alert level, no big issues. And this was for distance, which for thickness of 65 and 80 centimeters, which was the design. So we were following continuously with an automatic ways reporting temperature directly. Last issues. In fact, there was a dam effect, because in fact there is a big station on one side. Sometimes the level of water can change on one side, so go upward on one side, downward on the other side. And unfortunately, in fact, we were creating a neck here. And by creating a neck, what we did with fluorescent test, we saw that the water speed, the velocity of water, was up to 18 meters per day. And remember, it was a range where brine was maybe not working. So what we did, we sequenced, and the water was flowing into this layer, which is highly permeable. So what we did, we started freezing the soil by freezing only this layer. And then when this layer, which was highly pervious, was frozen, then we froze the remaining part of the soil, which was less pervious. And now, I won't go into detail, but you can see when it's blue, it's what we do. So the first step, we go with brine, duration 3 days. We start with highly permeable layer. When it's done, we freeze the full U. You can see that there is some upward movement at this location, P7. We stabilize and do a test. As I said, we did not have success in grouting this area because of low pressure, and we are very afraid of erosion because, in fact, the water was going downward into the excavation. So we were afraid that the frozen area was decreasing with time, and then suddenly we get flow. So we did an erosion test. This erosion test was done by draining inside the box, so putting the flow of water from outside to inside the box, going next to where it was frozen. And in fact, it was stabilized, so we didn't have to put more energy. Then we, in fact, froze this area. So we had kind of upward movement always, it's pile 7, so column 7. Excavation of the top of the box. Excavation inside the box. So you see that this is quite stable. There is no uplift. This is how it works, seen from outside. And this is the face. Very hard to excavate with a grinding machine, hydraulic hammer. As we were very close to the pipe, hydraulic hammer was not used, but the mill machine was, or grinding machine was used. This is, in fact, the column for temporary works, the excavation of the box. Now we had a problem with decreasing the thickness at some point, but we were able, in fact, to maintain. Doesn't work, yeah. So I won't go into this. People will have the PowerPoint?
Yep.
Okay, so I won't go into this. In 2 words, in fact, we had to adapt because the thickness of the frozen area decreased drastically next to the boxes. So we were, in fact, obliged to change the pipes. In the inner pipe, as you see, initially, it's always done like this. We have the outer pipe and the inner pipe, which gives the flow, the maximum cold at the top, at the bottom. We were obliged to cut the pipe by 2 so that the minimum temperature was at the middle of the pipe. And by changing, we were able, in fact, to increase the thickness of the area which was next to the wall. Excavation, casting the beam, and as you see here, the roof is maintained on jacks. Why? Because, so this is the top, the barrette. So barrette which is going to be cut in the middle. As you can see, the barrette was cut, and as the barrette was cut, we wanted to control, in fact, the settlement of all these piers. It was on jack, and for duration where the contractor had finished his work, and we were sure that it did not move anymore. So in fact, the contractor had to cancel, in fact, the frozen area by injecting brine, hot brine, at 20 degrees, 30 degrees, 40 degrees, to force the soil which was frozen to become unfrozen, because this is a question of guarantee, and this is a question of filling the jack. So we adapted the roof until there was no freezing area, excess pore water pressure was dissipated, and then it was sealed, and the contractor had finished, and the guarantee started at this point. So you can see the jacks, the barrette, which is on the side. Again, the jack, and we were able, in fact, to lift the box above to compensate for the vertical displacement. You see the joint of the slab between fixed top slab and the moving top slab, just at the location of the barrette which was cut. Okay, then when we had the thawing, everything decreased, so the settlement went down. And this was the end of the project with the rail system put in place. The barrette, which stayed, one of the barrettes stayed, the other, but this barrette goes into the tunnel and is able to slide inside the tunnel. And there is a water stop system which allows the barrette to slide in the box. So our conclusion. Yep. So it's a very powerful method, but we need, this is based on observation. So this is a way we need to follow, in fact, the site very carefully and adapt. So this is an interesting thing. There is not a lot of construction where observation is done, except some tunnels. It's an easy method, but if you don't make sure that there is no hole, there are many projects where all non-frozen area remain, and if you don't see and discover it, it's a big disaster. So it seems very easy, but this is really a control using, in fact, instrumentation, which is necessary. So it's observation and obviously instrumentation, which goes to observational method. A lot of adjustment. We need to compute because at the end, as we have thermocouple, which are not in large numbers, but enough so that the calculation and what we measure can be compared, we need to check by calculation that there is not an uncertainty or a divergence between what we measure at locations and the calculation. And in fact, the success is expert contractors, very reactive contractors, and engineers also to adapt to any non-anticipated behavior. This project, we had a lot of subjects. It took not so long time, but we had to adapt. We had sand coming. We had a lot of things coming. But at the end, it worked mostly on time with a safe project. So it was on time.
Thank you very much. Are there any questions? You've got a... We'll just have a couple.
Mohammed Al-Din Arcadis. So how many questions can I ask? So thank you very much for that great presentation. It was really great. So first question, just try to visualize, try to imagine this creep in the frozen soil, right? So creep in normal soil, it's kind of rearranging for the particles under constant stress, right? So we have a freezing soil where we can see this reduction in strength with time. Is it the same mechanical properties like the normal soil? Is there this kind of rearranging of the particles with time, or it's different?
In fact, you have different tricky phenomena which come with frozen soil. You have rearrangement, but in fact, you have the cement or equivalent cement, which is water, which behave differently. The ice behave differently. And when they see it on lab microscope, in fact, you have the different three state of free. But it treats also treat, but the change with time, let's say, like any material. But the amplitude of trick is very important here compared to solid. But by the way, when we do UCS and so on, we know that speed of test is important. But important does not go, you don't divide by 3 the result. Here you have to divide by 3 because you see it. You see it on site, like moving.
So second question, it's more practical question, right? So in many cases, we used pressure relief pipes just for this excess or this trapped water pressure. Do you use it all the time, or in some cases you will use it, some cases you will not? How can you evaluate this?
You always use it. Sorry? When it's a closed section, when the frozen area is closed, you always use it because this is one way of knowing that there is no hole in the frozen body. What is difficult is when the frozen body is not closed, because you do by calculation check that it works, but in fact you have no certainty. But so we always prefer that it's closed.
Sorry, can I just ask you so that the microphones that people online can hear?
All right, sure.
Thank you very much.
Okay. Another question there.
Mike McConnell, retired from Balfour Beatty. Very interesting indeed, Christian. Very quick one. It's the contractual situation and the complexity of the interface between what would traditionally be called temporary works and the main actual design of the tunnels themselves. And I'm just wondering if you can indicate in some way the way SYSTRA and there was another designer, I guess, also involved, and the contractor, as to who was really taking the design risks. I don't think I've ever seen a tunnel described with such a close interface between the actual permanent works design and what you're doing on the
consultancy side. In fact, on this contract, we signed the document. So the contractor is proposing. So this is what we call a specific contract type in France, where the contractor is proposing a solution. This solution is endorsed by the engineer, and if something goes wrong, it goes wrong, obviously, for the contractor, if it's not 100% what was done, what was supposed to be done, but also our responsibility is engaged. So if we accept the project, in fact, the responsibility is kept on our side. So this was the case, and this is why sometimes we say no, or yes. This is why I said sometimes. Most of the time we say yes, because there is no reason. But sometimes when we do believe the risk level is too important, then we say no, we don't want to do this. And for example, we said yes at some point where we had some problems. I don't tell the full story, but this is a story. But on some grouting issues, for example, under the slab, we were not really in agreement with the main contractor, but we said, okay, let's see if he's right. Because in fact, the risk was low. Yes, so if we do believe that for the final client, so for our client, the alternative solution is worth taking not the risk, because this is a measured risk and controlled risk, but if the solution is more adapted, because obviously everybody has its own way of thinking, and it's always better to optimize a project when the project is already done one way, as you know, because as a consultant, we start with the white page, and we have to do a project. On the contractor side, the project is done one way, and then you can imagine other solution. It's different, you see, and and everybody has its own schedule. We do a project, we choose a solution in a given schedule. This is a solution we see standard, and the contractor, in most countries, the contractor does an alternative, which is validated by the engineer. But the risk still in France lies on the consultant, but also on the owner, because at the end, we are not paying if there is something.
Any other questions?
Usually you are not paying. Sometimes we are paying.
One at the back there. We'll make this the last one.
Make it a quick one. Mark Westbridge, Zügle, UK. What percentage of salinity had the brine that was used for the Africa and Paris project?
The brine was, in fact, what we call the temper, which is a registered mark. I don't know if we can say it, but anyway. So it's a temper product.
Yeah.
Okay. Thank you very much.
Thank you.
We've just got a couple of any other business slides. First one, which you'll all like to know, is that the drinks are being kindly sponsored tonight by SYSTRA. So thank you very much for that. What you'll also like to know is that Tunnel Skills are sponsoring the sausage and chips. And those are the current members of Tunnel Skills. We are always, because I'm also involved with Tunnel Skills, we're always looking for additional members. So if there's any organisations here that would like to join Tunnel Skills in the development of qualifications of various forms for the tunnelling industry, please get in touch, either through the website or there is a link on the BTS website. So again, thank you very much for Tunnel Skills for sausage and chips tonight. Moving on, the next meeting, and please put this in your diary, we always have this one slightly earlier in February because it's a joint meeting with Min South. So it's on Thursday, the 8th of February. So you've only got a couple of weeks to wait to the next meeting. At the moment, well, on the slide there, it says to be confirmed. Well, hot off the press, we've had some problems because of the original speaker's company, unfortunately, went into receivership. We've literally this afternoon secured another speaker, and this is going to be on the Hong Kong CLK, Innovation and Challenges of Subsea Tunnels. Very kindly stepped in at the last minute, and that's by Boy TP. So that's hot off the press, and we'll update the website very shortly to show that. The week later, 15th of February, young members have a presentation on how to demonstrate competence and safety in tunnel design, exploring the role of guidance and standards. These are all in person here, starting at 6 o'clock. Of course, tea and biscuits beforehand.
Sorry, just a note on that one. It will not be live streamed for that one.
Right, okay. So yeah, no live stream on the 15th of Feb. 21st of March, that'll be the Harding Prize. We've got all the presentations in, and we're going through a review and scoring of the presentations. So we'll be announcing the successful presenters shortly, and then we'll have them on the night, and then we'll be additionally scored for their actual presentation skills. So we look forward to seeing what presentations they will be. But again, we'll get them on the website as soon as we can. April, Thursday the 11th. This is, again, a young members one. This is design and construction of Canterbury Works vent shaft on HS2. Week later, 18th of April, a joint meeting with BGA, Kilsby Tunnel construction, geotechnical and groundwater lowering. You'll all love to know that the dinner is on the 10th of May, the annual dinner 2024. The website for bookings will open shortly. It should be on the 1st of February. So look out for that and get in early for a table. The other booking that's going to open on Monday is for the design and construction course. Spaces are limited this year because of availability of rooms at Warwick University. So again, first come, first served, and when we get to the limit, we're at the limit, whereas normally we can accommodate people right up to the end. So that's all the slides, the final one being, that's how to find out any other information. Sorry, question?
Ron, could I just briefly ask the status of the BTS anniversary book? Many of us have completed a lot of text many years ago now. I've even got some friends in New Zealand who are on tunnelers and want to, on their Christmas cards now on an annual basis they're asking.
Right,
Is the ICA printing system or something?
right, it is getting printed, not just yet, but you will be allowed to secure your books in late February. There's be an ordering system, and you'll be able to reserve your book, and then we'll be able to update everybody. So there'll be information about that in late February, and you'll see it in various TNT and things. But there'll be a pre-ordering arrangement that's going to be set out in late February.
Has a printer been agreed?
Yes, we've got a printer and everything. Yes, it's not the ICE. The ICE has changed its printing arrangements, and its original printer has changed. So we've had to go to somebody else. But yes, it is imminently there. Okay, thank you very much. The bar and food is now open, and look forward to seeing you next month.